Okay, welcome everyone to this afternoon session if you are on the East Coast, and just before the lunch session if you're on the West Coast. We've got an exciting program for us today. If you have any questions for the speakers, please post them on the Slack channel. I'll do my best to get through as many questions as possible, but given the time constraints, we'll probably have 2 or 3 questions with each talk. So first up, we have a talk on the assembly history of lenticular galaxies by Ariana Dolphy, who is at Swinburne University in Melbourne. Ariana, please take it away.
Thank you. Hi everyone. So first of all, thank you to the organizer for giving me the opportunity to talk to this meeting. And thank you to everyone who joined today, both in person and on Zoom. My name is Ariana. I'm a third-year PhD student at Swinburne University of Technology. And today I'll be talking about my PhD project that focuses on studying the assembly history of L0 galaxies from the large 3D-eye kinematics. So lenticular galaxies, you can see them here between elliptical and spiral galaxies in the Abel-24 diagram. These galaxies that show no evidence of spiral arms nor star formation. Early studies had found that the fraction of L0 galaxies is increasing between redshift 0.5 to redshift 0 in rich galaxy clusters, while on the other hand, the fraction of spiral galaxies shows the opposite trend as they are decreasing going from redshift 0.5 to redshift 0, while the fraction of elliptical galaxies remains roughly constant as a function of redshift. This has therefore suggested that lenticular galaxies could be an evolution of spiral galaxies in galaxy clusters as a result of environmental processes. However, lenticular galaxies are also observed in low-density environments where the interaction with the environment are limited or non-existent. This therefore requires additional formation pathways and physical processes to the formation of L0 galaxies. And these physical processes may include like merger events or circular evolution or gas accretion. And each one of these physical processes is expected to produce L0 galaxies with different kinematic properties out to large 3D-eye. For instance, while measured mergers are expected to spin up the rotation of the stars at large 3D-eye, minor mergers are expected to spin down the rotation of the stars at large 3D-eye. On the other hand, a circular or passive evolution is expected to produce L0 galaxies with higher stellar rotation at large 3D-eye that retains rotation from the spiral progenitor, or in an accretion of gas onto a compact elliptical galaxy, the newly formed stars are expected to have higher rotation as opposed to the old, more dispersion-dominated stars. So it is important to reach out to large galactic-centric radii in order to distinguish between all these different physical processes. Also, because it is a large radii where signatures of merger and accretion events are better preserved due to the longer dynamical timescales of the galaxies. So in my initial project, I've selected a small sample of L0 galaxies from the SLAG survey. This sample contains specifically 9 early type galaxies, all showing evidence of a disk-like components. You can see them in the figure in the colored boxes. And these galaxies are all mainly located in low-density environments, so in the field and small groups. There is only one cluster galaxy highlighted in the green box. And these galaxies were selected based on the number of globular clusters and planetary nebulae that had available measured radial velocities from the literature. So for all these galaxies, we combine the kinematics of the stars, globular clusters, and planetary nebulae in order to study kinematics of the galaxy out to large radii, so really out to 5 effective radii. In 6 of these galaxies, which we here refer to as aligned galaxies, we find that the globular clusters and planetary nebulae were kinematically aligned with the underlying stars, meaning that the axis of rotation of the globular clusters and planetary nebulae was roughly consistent with the axis of rotation of the underlying stars, which was also at the same time roughly consistent with the photometric measured axis of the galaxy. And at the same time, the rotational velocity of the globular clusters and planetary nebulae was also overall consistent with the rotation velocity of the stars. This plot shows the average V over sigma profile as a function of the galactocentric radius, normalized by the effective radius of these 6 aligned galaxies. The average V over sigma profile is obtained by averaging the individual viewer sigma profiles of all the distinct tracers. So globular clusters, planetary nebulae, and stars in the overlapping radii to reach out to 5 effective radii. And for these galaxies, we measured the viewer sigma gradient between the outer and inner regions. And we compare these values with the values from the simulations that are shown in the inset plot here. These values in the simulations were adopted to distinguish between 3 characteristic profile shapes. Profile shapes that is increasing, that has viewer sigma profile increasing out to large radii, a profile shape that remains roughly flat out to large radii, and a profile shape that is peaked and outwardly decreasing out to large radii. So in the comparison with the simulations, we then classify 4 of our galaxies as peaked and 2 of our galaxies as flat. On the other hand, the remaining 3 galaxies, which we here refer to as misaligned galaxies, had globular clusters and planetary nebulae that were not kinematically aligned with the underlying stars. Specifically, the planet in NGC 821 on the left, the planetary nebulae in green were kinematically misaligned with the underlying stars at all radii, while in NGC 4649 in the middle, the planetary nebulae and blue globular clusters showed a twist in the kinematic axis of rotation beyond 2RE, where the rotation of the globular clusters and planetary nebulae was increasing again. And finally, NGC 5846 on the right showed very little to no rotation at all radii. So how did these galaxies form? For the 6 aligned galaxies, we suggest that the 4 galaxies with peaked and outwardly decreasing viewer sigma profiles are likely the result of late mini mergers that enhance the velocity dispersion of the galaxies at large radii, leaving the kinematics of the central regions of the galaxies unchanged. On the other hand, the 2 galaxies with flat viewer sigma profiles are likely the result of late minor mergers that also influence the kinematics of the central regions of the galaxy, specifically erasing the central peak of rotation. On the other hand, for the 3 misaligned galaxies, we suggest that they're likely the result of multiple late minor mini mergers that enhance the velocity dispersion of the galaxy at all radii, while only NGC 4649 is most consistent with the late measured merger that spun up the rotation of the globular clusters at large radii. So in my current project, I'm now using the EMOSEC simulations to study the kinematic properties of the globular cluster systems of a sample of simulated L0 galaxies. And the aim of the project is to understand how the kinematic profiles of the globular clusters are correlated to the specific assembly history of the L0 galaxies. So I'm using the EMOSEC simulations, from which we select from the visual inspection 50 L0 galaxies, all showing quenched star formation that have stellar masses in this stellar mass range, log stellar masses between 10 to 11.5. And all these galaxies are located in low density environments. So they match the environments of our previous samples from the observations. So similarly to our previous work based on the observation, we separate these galaxies between aligned and misaligned, depending on whether the kinematic position angle of the globular clusters is consistent with the overall photometric position angle of the galaxy. We find that 44 of these galaxies are aligned. And for these galaxies, similarly to how done before, we calculate the viewer sigma gradient between the outer and inner regions of the galaxies. In this plot, you can see the viewer sigma profiles as a function of the galactocentric radius normalized by the effective radius of the galaxies. And so we classify these galaxies into the 3 characteristic profile shape of peaked and outwardly decreasing on the left, flat, and increasing on the right. We find that, overall, we find that the peaked and outwardly decreasing viewer sigma profile seem to be the dominant profile shape, suggesting that the formation pathway through late minor and mini mergers could be the dominant formation pathway for the formation of L0 galaxies in low density environments. On the other hand, for the remaining 6 galaxies, we classify as misaligned. These galaxies are shown here. In the top panel, we show the kinematic position angle of the absolute difference between the kinematic position angle of the globular clusters with respect to the photometric measured axis of the galaxy as a function of the galactocentric radius normalized by the effective radius of the galaxy. And the bottom panel again shows the viewer sigma profile as a function of the galactocentric radius normalized by the effective radius of the galaxies.
2 minutes, Carol, 2 minutes.
Okay, thank you. So from the viewer sigma profile, one thing that we notice is that some of our galaxies show this characteristic double peak V over sigma profile. So a viewer sigma profile that has a central peak that decreases to large radii and increases again a large radii, which resemble the viewer sigma profile of our previously observed L0 galaxy NGC 4649. And this could suggest that these galaxies could as well be consistent with being the result of a late measured merger that spun up the globular clusters. The rotation of the globular clusters at large radii and possibly caused the misalignment. So these though are still preliminary results, and the next step would be now to compare these kinematic profiles with the merger trees of the L0 galaxies from the simulations in order to understand how these different kinematic profile shapes, viewer sigma profile shapes, are linked to the different assembly history of the L0 galaxies. And so here are my conclusion, which I'm happy to leave here and take any questions. Thank you for listening.
Wonderful. I hope you can all join me in applauding for Ariana, even if you're remote. Let's open it up for questions. I'll mention the questions that are on the Slack. So the first question that I see is from Ryan Burley. He says, this might be a simple thing, I don't know, but what causes galaxies to be misaligned?
Well, yeah, we're actually now looking into this. And so we're now looking at the merger trees of the galaxies to try to understand what is actually causing this misalignment, and if the galaxies that we identified as misaligned have specific, peculiar merger trees compared to the other galaxies. And from a first look, it would actually seem that it is not a late measured merger that is causing the misalignment. So it could be due to other properties of the mergers, perhaps the orbital configuration of the merger that is causing the misalignment. However, yeah, I don't have an answer. We are still trying to look into this.
Okay, thank you. While you stop sharing that screen, I'll read out the next question and then Caro can set up. So the second question I have here is from Amelia Fraser McElvey. She says, nice talk. Do you have deep imaging of your slugs galaxies to search for merger remnants and confirm your theory of merger-driven formation?
It's a good question. Not that I'm aware of. That I'm aware of, there are not. I don't think there are deep imaging for all the galaxies, but I can double check and get back to you.
Okay, that seems like a good reply for on the Slack. We have time for one more question, so I'll pose the question from Luca Cortese. He says, sorry if I missed it, but I was wondering if you have any plans to extend this study to early type disks to see if you find the same diversity of behavior in this V over sigma profiles. So do you plan to also look into early type disks, meaning SAs or SAB galaxies as well for your study?
For now, I haven't thought about it. For now, yeah, I was focusing on zeros, but yes, that's I guess yeah, it's a good point, and yeah, I could. I can think about it.
Okay, excellent. I hope you can all help me thank Ayana for that wonderful talk and replying to all the questions. There are many more on the Slack, so I encourage you to have a look there. The next talk we have is from Caro Derken, who is at Macquarie, and she'll be looking at the density slopes of early type galaxies. Caro, take it away.
Okay, hello everyone. Thanks for joining this talk. I'm from Macquarie University and my supervisor is Richard McDermott. And I'm talking today about the density slopes of early type galaxies. And so for this work, I would like to acknowledge the help of Adriano Pocci, Rhea Silvia Remus, Eric Amselem, and Inga Jorgensen. On the background of this slide, I actually have one of the clusters that I studied as part of this work. And just for fun, I'm going to point out my favorite galaxy in the sample, which will pop up a little bit later on as well. So before we really get into it, what actually is a total mass density slope? Here I have a figure from the Magneticum simulations, which shows the density on the y-axis and the radius on the x-axis. And because these are simulations, we can actually break down the density into its contributors, so the dark matter and the stars. And you can see that the dark matter starts to dominate at large radii, and the stars dominate at small radii. But the interesting thing is when you combine those two things, you actually get this fairly constant profile, and we call that the total profile. The slope of this is the total density slope, and we give that the symbol gamma. So total density slopes can be quite steep at -3. They can be quite shallow, and that would be a common value of -1. And we call an isothermal solution a gamma value of -2. So why are total density slopes important? Well, for that, we actually need to turn to the simulations. So the Illustris TNG 100 simulations show that total density slopes were quite steep at higher redshifts, but then they quickly approached isothermal values, so about -2 in the local universe. The Magneticum simulations have steeper slopes at higher redshifts, and then they gradually again approach those isothermal values. So even below redshifts of 1, there's actually a redshift trend of the density slope approaching those isothermal values. And this actually points to a 2-phase evolution. So at early times, there was lots of in situ star formation occurring, and that meant that galaxies had high density central regions. At later times, dry mergers increased the radius of the galaxy without increasing the mass too much, and so the density slope became more shallow. So a total density slope is really a probe of the evolutionary pathway of early type galaxies, and it also correlates with other interesting things such as dark matter fractions. In the local universe, dynamical modeling has been really effective at measuring total mass density slopes. So one of the main measurements was the ATLAS 3D sample. So that was 258 early type galaxies, and they used dynamical modeling to measure those total mass density slopes, finding just steeper than isothermal values. That went out to about a radius of 1 effective radius. Then the slugs, a subset of that sample using slugs data, was extended to about 4 effective radii with comparable results. And then we have the MENGA sample, which is the largest sample, but that wasn't just restricted to early type galaxies. But you can see that this convergence towards isothermal solutions in the local universe is in agreement between observations and simulations. But at higher redshifts, historically, gravitational lensing has been used to measure total mass density slopes. It's harder to apply dynamical modeling out at these redshifts just because the galaxies get smaller, fainter, and cosmological effects start to play against you. And with the gravitational lensing total mass density slopes, you can see that at 0.1, 0.2, 0.3, they all kind of agree with these isothermal solutions. But when you take the trends up to 0.6, 0.8, and 1, we actually see the opposite trend as predicted by the simulations, in that at higher redshifts, the total mass density slopes were actually more shallow. And Bolton finds the steepest relation of d gamma dz of about 0.6. So this is pointing to an observationally different evolutionary pathway, something like continued significant gas accretion or potentially off-axis major mergers. So this is where my work comes in, this discrepancy between the gravitational lensing results and the simulations. Maybe we can resolve this by pushing dynamical modeling, which has been so effective in the local universe, to these higher redshifts. So to do this, I needed a good sample of early type galaxies, and this is where the frontier field sample comes in. So there are 6 clusters in total, but I only used 5 that had optical MUSE data. And this is a really rich data set because it has deep MUSE data, up to 10 hours integration time, and it also has overlapping Hubble fields, which is really important. And the seeing went from beautiful for the MUSE data of about 0.6 arc seconds to not so great with, unfortunately, the high redshift cluster about 1.5 arc seconds. So for the dynamical modeling, you need a few inputs. We needed the kinematic fields and also a measurement of the luminosity density of these galaxies. So we fit 2 moment fits define the kinematic field, so V and sigma, and then this is turned into a single VRMS field via a quadrature sum of these fields. So I show here one of the aperture spectra for this galaxy, and that was used to create a template for the other 2 fits. And then this is my favorite galaxy in the sample, again, popping up here. And we also found through Monte Carlo simulations that we could actually constrain the density slope even for cases where we only had 5 kinematic bins per field, but below that we could not constrain the density slope. Then the Hubble photometry came in to estimate and measure that luminosity density of the galaxy, so the luminosity potential. So this is an example of one of the multi-Gaussian expansions that we did using the Hubble data. So this is an example of the Hubble data here as well. The main comparison sample that we had for this work in the local universe was that Atlas 3D sample. So we actually set up the models in an identical way to that to make it a really fair comparison. So here we use the GEANS anisotropic modeling. So it has an anisotropy parameter, which is characterizing the tangential and radial components of the velocity dispersion. We only actually need the density and the inner slope to characterize the total profile, but we included the anisotropy and the inclination just so that our uncertainties would be a bit more accurate. So here we have a VRMS field of one of the galaxies in the sample. You can see it gets a little bit noisy out on the outskirts. And this is the JAM model of that field with the best fit parameters. And we use the Bayesian inference sampling technique in Python implementation MC to do all of our uncertainty estimation. So this is what we found. The green points are the points from this work. Unfortunately, like I mentioned, our highest redshift cluster actually had some of the worst seeing conditions for the MUSE data. So we weren't able to find that many galaxies in that cluster that met our criteria for reliably being able to constrain the slope. But I think one of the takeaways from here is there's no evidence of that uptick that you see from the gravitational lensing points. But let's take a look at these distributions in a little bit more detail. So on this panel, I show a comparison between the observations using the frontier fields galaxies and the Magneticum and Illustris TNG galaxies within the same redshift range. So this is about 750 galaxies for Magneticum and about 1,400 galaxies for Illustris TNG. And it's actually quite striking. You can see that the Magneticum prediction of the total density slope at this particular redshift range really matches up with what we're seeing in observations. But on average, we find that the Illustris TNG galaxies are a bit more shallow, have more shallow density slopes. So this panel shows the cumulative distributions of the total density slopes. And we actually performed a KS test on this, and we could not reject the null hypothesis that the frontier fields and Magneticum density slopes come from the same distribution. So that was really interesting. On the right, I show the comparison between the frontier fields galaxies and the Atlas 3D galaxies. And as you can see from the cumulative distributions here, they really quite well agree. So what this is suggesting that in the past 4 to 6 gigayears of cosmic time, evolution that these early type galaxies have undergone has been in a way that has not changed the total density slope. So here we see the total density slope being around isothermal as an attractor. So it's this high entropy, low energy solution that galaxies tend to converge towards. And this is also supporting a picture of dry merging as a way that early type galaxies are increasing their mass and radius. We also tested for correlations between the density slope and other structural parameters of the galaxy. So this was also quite interesting because the Magneticum simulations predict quite a steep relationship between effective radius and the density slope, but there was no significant relationship between effective radius and density slope in the frontier field sample, quite similar to a zero slope in the Atlas 3D sample. We found a similar relationship with the dispersion and the density slope between the frontier fields and Atlas 3D sample, in that galaxies with a higher velocity dispersion tend to have steeper slopes. And this was the most striking one with the surface mass density, because not only do the Atlas 3D sample and the frontier field sample both show quite similar relationships, the Magneticum simulations also show this same relationship. And this is actually identical to one of the gravitational lensing relationships. So surface mass density seems to be quite a strong predictor of what's happening, of the total mass density slope.
2 minutes, Carol, 2 minutes.
Thank you. I would also like to reiterate that it's interesting that these Atlas 3D relationships and the frontier fields relationships are quite similar because they are across different redshift bins. So this is suggesting that these redshift trends are not actually, these density slope trends, sorry, are not actually changing with redshift. So a caveat to this work, and something that we should keep in the back of our minds, is that all of this work was actually done in the context of these very dense cluster environments, and cluster environments can change the evolution of galaxies, with older populations being preferentially found, for example, in higher density regions, and also things like interactions and dark matter halo truncation going on. So the question is, could this actually impact our knowledge of the distribution of density slopes? So this is where the MAGPIE survey will come in. In particular, you can see the velocity and velocity dispersion fields here that are of such good quality that we'll be really able to disentangle the role of environment with this sample. So I'll leave you with my conclusion slide, and the paper that accompanies this work was actually just freshly accepted on Friday, so you can find it up on arXiv now. Great, any questions?
Fantastic talk, Carol. Absolutely wonderful. I'll go to the Slack for the questions. So there is a lot of activity, so we won't be able to go through all 8 or 9 questions and comments. So I'll do a little bit of a selection. The first one came from Matthew Collars, and it said, is it clear that the apparent increase in the total mass density slope at high redshift is not a selection effect or measurement bias of some sort?
That's a really interesting question. So the Magneticum simulations actually looked into this, and they found that when they put simulated galaxies through the gravitational lensing pipeline, they found artificially shallower slopes. But that work wasn't really continued, so we don't know what particular reason that was happening for. But if you think about the bias, I mean, gravitational lensing galaxies are the most massive dense objects that we have, because then they can act as lenses. And if that were the case, these massive dense objects, you'd expect to have really steep slopes from the trends that we actually found. And that they have more shallow slopes is kind of counterintuitive to what we would expect, given what we know about the potential biases in those samples. So definitely more work to happen there. But really, we also want to push out to higher redshifts with this technique. Like 0.5 was good, but we need to go higher.
Okay, great answer. Whilst you stop sharing your screen and Sam sets up, I'll read out the next question. I'm just going to pick a student question first. So Julia Santucci asks, just wondering, is your anisotropy parameter fixed with radius, or are you assuming a radial profile?
Yeah, we just assumed a fixed anisotropy. And I should say, for the most part, it was not constrained by the models. But we found that when we didn't include it in the models, our uncertainties became a bit unrealistically small. And so we just kind of included it for the most part as a nuisance parameter, but in some cases it was actually constrained, but global, not radial.
Okay, we've got time for one more question. This one came from Carl Glazebrook, and he asks, is the convergence to isothermal at redshift 0 theoretically explainable? Meaning, galaxies approaching a dynamical equilibrium?
So that's the theory. It's kind of a semi-relaxed, incomplete relaxed state. I think for a more detailed answer on that, the work that really goes through the maths of it is the 1967 Lyndon-Bell paper. But it is thought to be this sort of high entropy, low energy, relaxed kind of state. Yes.
Okay, somewhat related on this same topic, a question from Sabine Bellstadt. How concerned are you about the fact that for this sort of modeling, we're still generally limited to assuming a spherical dark matter halo?
Yeah, that's a really good question. It's not something that we've tested. I know that in Capillary's 2015 paper, there was some tests done about, is it a good descriptor? And some other works have done that as well. It's also a playoff between how much information do you have in the kinematics to support more complicated models, and you don't want to start inferring things that your data doesn't actually support. So I think for now, simple is okay, but definitely more work to be done there in the future.
Okay, thank you, Carol. Please join me in thanking Carol once more for answering all of those questions, and welcome Sam to the floor. Sam will talk about the universal metallicity gravitational potential relation using SAMI data, and Sam is a postdoc at the University of Sydney. Sam, please take it away.
Thanks very much. So yeah, my name's Sam Vaughan. I'm a postdoc at the University of Sydney, and thanks very much for coming to my talk. So I'm just going to start off by speaking a little bit about what we can learn from studying the stellar populations of galaxies. A brief chat about measuring stellar metallicities and the slopes of galaxies. And then also the main part of the talk is going to be talking about a kind of simple model of galaxy evolution I've been using. Okay, so why are stellar populations useful? So it's fairly clear that the present day metallicity and age of a galaxy give us clues about its formation history. We think that metal-rich galaxies have undergone different things in their lifetime than metal-poor ones. Recent work has shown that, or discussed the idea that metallicity relates to a galaxy's quenching timescale. So for galaxies which are quenched and aren't forming any stars anymore, people have argued that their current stellar metallicity tells us how long that kind of quenching process took. And we've also seen in many simulations that steep gradients are expected from a simple kind of monolithic collapse scenario, where one big gas cloud turns into one big galaxy. Whilst galaxies that have undergone a series of minor mergers and accreted satellites tend to flatten out their gradients in the outskirts. So they really do contain a lot of information which we'd like to know about. So we can measure stellar population properties by studying the spectra of galaxies. Not going to go into too much detail here, but here's a quick example. In black, you can see a single SAMI galaxy spectrum, and red is my fit to that data. The idea is we kind of build a model galaxy ourselves by adding in different templates with different metallicity and age properties, and then we tweak the parameters until we get a good fit to our data. So I've been doing this for almost 2,000 galaxies in SAMI, and I've been doing it in a spatially resolved manner. So here is an example of a galaxy in SAMI. On the left, you can see the SDSS POSIS-SAM image, this very kind of blue disk and red bulge in the middle. In the middle, you can see the light-weighted age measurements I make, and on the right, you can see the light-weighted metallicity. So all of these different kind of pixels here have different measurements. They all correspond to one spectrum. In the middle, a single spectrum is high enough signal to noise for me to look at that on its own, whereas I've got to bin a bit more in the outskirts. But everything here has a signal to noise of 20. And yeah, so this ended up being 80,000 spectra from nearly 2,000 galaxies from SAMI. So now I'm going to focus pretty much on metallicity. So I've made metallicity maps for each galaxy in my SAMI sample. I'm now measuring their metallicity gradients as a function of radius, obviously. So to do this, I've got a straight line to the metallicity as a function of radius. One perfectly good way to do this is to take each galaxy on its own and just say, okay, I'm going to fit y represent x plus c, and write down the gradient and write down the intercept. But we actually have quite a lot of prior knowledge about the gradients and intercepts of galaxies. We know, for example, that a very massive 10 to the 11 solar mass galaxy is very unlikely to be metal poor. in its center. And similarly, a kind of low mass galaxy is very unlikely to be pushing a metallicity of plus 0.4 dex. So I've tried to incorporate this prior knowledge into what's called a Bayesian hierarchical model. The idea here is that I'm still fitting straight lines to each galaxy individually, but now the priors on the slope and the intercept vary slightly for each galaxy. So the prior on the slope depends on the galaxy's stellar mass, and the prior of the intercept depends on the galaxy's stellar mass and its star formation rate. So I've used these relationships because previous work has found that star-forming galaxies have different metallicities to their quiescent counterparts at fixed stellar mass, and other work has also studied gradients as a function of stellar mass. But there is one key thing to note here. These prior dependencies are estimated from the data itself. So I'm not putting in anything by hand. The linear relationships between the prior and the quantities I mentioned, all those, the parameters for that are estimated from the data itself. And so you can just have equal priors for every single galaxy if that's what best fits the data. Okay, so to show you guys that I'm not talking complete nonsense, here's an example of 5 different galaxies I've just picked at random. And the blue line is the best fit metallicity slope. And then if I look at my sample as a whole, you can see here, this is the mass size plane of my galaxies. So that's size on the y-axis and mass on the x-axis. And the color bar here shows the central metallicity. So that's the y-intercept of my data, the metallicity at r equals 0. Yeah, and you cover this really nice trend, which has been seen before in various studies. One thing I should say is that I'm not applying any smoothing here, and these are results that come out of the model. But of course, my kind of Bayesian hierarchical model does apply a bit of a regularizing effect itself. One last thing to mention is that I have, of course, done the kind of standard thing of just fitting each galaxy on its own, and we get very similar results if I do that. Okay, so now let's look at the mass metallicity plane and what I'm calling the potential metallicity plane. So on the left, you can see the metallicity on the y-axis and stellar mass on the x-axis. Points in blue are currently star-forming galaxies. Points in red are currently quenched and passive. And then yellow points are kind of green valley galaxies somewhere in between these two things. And what you can see, the large points there are just a kind of a binned median. And what we find is that there's the offset in metallicity at fixed mass, which has been well studied before. We get very similar results to other work. The main thing is on the right, you can see the relationship between metallicity and this thing I'm calling potential. That's stellar mass as log m1r, or stellar mass minus the effective radius. It's not quite potential, it's something kind of a proxy for it. And yeah, now we see that all galaxies lie in exactly the same relationship here. i.e., no matter what star formation a galaxy has, if you tell me its mass and size, I can tell you its central metallicity to within a scatter of 0.1 dex. So yeah, we agree with previous work. This plot on the right matches very well with some work by Tanya Baroni in the past couple of years. So thinking about quenching timescales, previous work by Peng et al. And Trussler et al. Have said that the stellar metallicity tells you about how long it takes a galaxy to quench. The idea is that when a galaxy is forming stars, the stellar metallicity is always trying to catch up with the gas phase metallicity because stars are formed out of gas. Stellar evolution tends to increase the galaxy's gas phase metallicity as metals get returned to the galaxy's ISM, whereas pristine halo gas tends to decrease it. If you can cut off a galaxy's supply of halo gas, but allow it to keep forming stars in its disk, the gas phase metallicity will sharply increase. You kind of get a feedback loop. You stop diluting the gas, so the stars increase the metallicity, then you form new stars out of this metal-rich gas, which increase the metallicity, and so on and so on. So the idea is that galaxies will kind of evolve along the star-forming relationship, quench slowly, and then suddenly kind of move diagonally up to join the passive population here. That's what gives you this kind of offset at fixed mass. So I thought I'd like to investigate this with my own data and see how this fits in with the relationship between potential and metallicity. So I made a kind of simple toy model of galaxy evolution. Take a range of redshifts and give galaxies a stellar mass and a size. I assume that the slope of the potential metallicity relation is the same at high redshift as it is today. And that allows me to give galaxies a metallicity. I evolve galaxies forward in steps of 10 million years. And every 10 million years, each galaxy forms a set amount of mass such that they always stay on the main sequence of star formation. I assume that star-forming galaxies increase their size according to this simple relationship, which comes from a paper by Van Dokkum et al. And also various simulations. And then also, I assume they increase their metallicity to stay on the potential metallicity relation. So that allows me to track their mass, size, and metallicity as a function of redshift. Now, I have galaxies quench in a way which depends on their mass and also their size. Once a galaxy quenches, they stop growing in mass, size, and metallicity, so they just kind of stay where they are. And on the right, you can see a plot of the mass-size plane. I've made this grey shaded region to the right, which is bounded by a line of constant stellar mass, constant potential, and also constant surface mass density. When a galaxy crosses over into this kind of exclusion region, I give it a 10% probability to quench in the next time step. So the location of these regions is pretty empirical. I just did it to kind of match what I see in the SAMI data. But what I find is actually, if I do this, I get a really nice agreement with the data. So after this, I run the simulation down to today. I then sample my galaxies to have the same mass function as SAMI, add in some observational uncertainties as random scatter, and then compare to the SAMI centrals. And what we find is that I get a really nice agreement with the data. So the top row is the data of SAMI central galaxies. This is the mass metallicity plane, potential metallicity plane, and mass size plane. And then the bottom is my kind of simulation. And what I find is that I get a really nice agreement. I can pretty well recover most of these relationships just with my simple model. Okay, I'm going to leave out my conclusions and happy to take any questions.
Okay, thank you, Sam. Let's go to the questions. There's a question from Mike Kriel. Sam, what causes the intermediate galaxies to have higher metallicities than star-forming ones between a solar mass of 9.5 and 11.2, but lower outside of these ranges?
Interesting. I have to say I've mainly been concentrating on the star-forming crescent populations. So we're looking at the low mass end of the mass metallicity plane. Yeah, that's an interesting one. So the first thing to say, of course, is that there aren't many intermediate galaxies there. Perhaps that's perhaps there's some kind of scatter there. There's many more star-forming galaxies which scatter kind of up and down. But yeah, I've got to say that's not something I've thought about too often, too much. So it's perhaps an interesting telling us something about how low mass galaxies quench as well. So yeah, interesting, really good question.
Okay, thank you, Sam. So the next question I have is from Chin Ui, and they ask, is there any evolution of stellar age in the mass size plane?
Sorry, so how age varies on the mass size plane? Is that the question?
Yes. Is there any relation or evolution within the mass size plane?
Yeah, there definitely is. More massive galaxies tend to be older. I have a plot, not in this presentation, unfortunately, of exactly that age across the mass size plane. It's not. Yeah, I'm sorry. Probably have to wait till my next paper comes out with that plot in it. This is mainly just concentrating on metallicity, but happy to share that in the Slack if you're interested.
Okay, thank you, Sam, for that. We'll have time for one more question, and in the meantime, Angel, if you could please set up. I'll pick the question from Amelia. She asks, from your mass size plot, it seems like there are trends in both stellar mass and size for central metallicity. I understand why stellar mass is important, but why the size dependence, do you think?
Yeah, so great question. So an argument is that, okay, this is, I think, comes down, it's actually quite a deep question. The size of galaxies is turning out to be a much more fundamental parameter than I'd ever thought when discussing their evolution. So one kind of hand-wavy answer is that smaller galaxies at the same mass are going to have a deeper potential well, so can hang on to their potential, so hang on to their metals more easily than a similar mass galaxy, which is much more extended. Of course, galaxy sizes are also linked in some way to the size of the galaxy's halo, and so there's various physical processes which can affect the evolution of galaxy based on its halo size. So I wouldn't be at all surprised if that was important as well. But yeah, it's a very good question, which would be great to have an answer to.
Okay, thank you, Sam. There are many, many more questions on the Slack, but due to the time, we have to move on, unfortunately. So thanks many to Sam for answering all these questions. And we now also welcome Angel Lopez Sanchez, who is a senior lecturer at AEO Macquarie University, and who will be talking about the HiKids survey. Angel, please take it away.
Thank you very much, Jesse. Thank you, everyone. Also, thank you for inviting me for giving this talk about the work that I have been conducting during the last few years at the AET and using the KOALA instrument, the High KOALA IFS Dwarf Galaxy Survey. Let me give you a quick introduction. Because we have been listening to many different talks involving IFS galaxy surveys, and when we have to consider also it is that they usually are targeting the normal galaxy population, but dwarf galaxies tend to be massively underrepresented, particularly when we compare with volume limited surveys. The other important issue that I like to address it is that sometimes that they are targeting many galaxies, which is of course important for understanding statistically galaxy evolution. But one of the particularities that it is not possible to go deep into the faint emission lines, and that is quite important for metallicities, for example, for the gauge phase metallicities. Furthermore, many of the galaxies are relatively far away, so we cannot resolve very well the star-forming regions there. There was a very nice example using SAMI data that was analyzed by Sam Richards and in a paper in 2015. And also Brent Grove was talking about this when he was presenting the result from FANGS and H missing there, sorry for that. And in the majority of the cases, if there is H1 data, they usually are coming from single disk observations, and that is important because we need to understand all the processes that are happening for the star formation in galaxies, and we also need that important component that is the neutral gas of the galaxies and the galaxies. And I like to show that, for example, with this nice image of M83. Combining several in the optical and the ultraviolet, when you add the H1 data from the local volume H1 survey, and you see that there is plenty of gas there and how it is related to the different star formation, different star forming part of the galaxy, even in the outskirts of the galaxy. So we need a deep IFS dwarf galaxy survey that includes interferometric H1 data. And after the presentation that Sam just gave, that it was really, really good, I think I don't have to convince anybody about why understanding what is happening with the metallicity is also important for understanding galaxy evolution, because it is a way of connecting stars and gas. Metals is a way of measuring how much the gas have been processed into stars and informed about the star formation history and assembly of galaxies, as well as tracing the inflow of pristine gas, of outflows of processed gas, and many, many other things. I like to illustrate that with this image from my own research, and that is the galaxy pair NGC 1512, which is this part here, the blue dwarf compact galaxy NGC 1510, which is that thing there. It is a blue compact dwarf galaxy, not a star, that are two in interaction. In blue, the ultraviolet rich emission, plenty of that in ionosphere. In green, the H1 gas. Well, for this galaxy, I used the 2EF instrument at the AAT to map the metallicities and to get a spectrum of many of these star-forming regions in the outer-spheres. And I was able to trace the metallicities. And I found some interesting results. First, that the part here, this arm was very much enriched, more chemically enriched than the other arm. But even though the other arm already had a lot of metals before the star formation actually started. So that huge amount of gas that this galaxy has, it has still plenty of metals that are coming from the circumgalactic medium, perhaps even from dwarf luminosity was rich galaxies that have been slow accreted and destroyed into the system. So that is the aim of HyKITS, which is trying to target dwarf gas-rich nearby galaxies using the Koala instrument. And the API of this project, we have still very new web page, and we try to explore this parameter space that is usually not studied well with current IFS surveys. So we are using this Koala plus A omega instrument and trying to get all the optical range for getting the key emission lines. And the sample selection of the galaxies is using a galaxy for which we already have resolved H1 data, mainly from the local volume H1 survey from Barber-Korybatsky et al., and also some few for the fixed galaxies, and some few others that blue compact dwarf galaxies that I'm very interested in, that I observed at the compact array. And actually, that was a project that brought me to Australia 13 or 14 years ago. If you don't know the Koala HiView at the Anglo-Australian Telescope, let me give you a very quick overview. It is it stands for Kilofiber Optical AAT Lenses Array. It is an HiView very high efficient, mounted at the F8 Cassegrain focus, and it fits the omega spectrograph. It has 1,000 hexagonal lenses, and you can select different field of view. The fill factor is very good. It is actually 97, 98%. So that is actually very important also for this kind of analysis. We are using A omega, that is a double beam spectrograph that we can select the wavelength coverage and resolution. It is the same spectrograph that have been used for SAMI. And just for a quick comparison, that is the Koala field of view when you compare with the Muse field of view at the VLT, 39% of the Muse field of view with this instrument. However, because we are using A omega, we can push it to the very blue end. And I will say something else about that later. So the current status of the survey is that we have observed 72 galaxies using 220 points. We will release all the data when we finish the survey in AAO data center. But what I have to say is that the majority of the time, besides observing during the last few years, have been trying to create the PyKoala, which is this new Python pipeline to reduce Koala data. And that is why, if you don't mind, I'm going to show you very briefly what this does, because I still cannot show you very results from all different galaxies. It is just working with this, thanks to Macquarie undergraduate students that we get from to prepare the RSS, the raw stack spectra that usually provide from 2D FDR using all different calibrations, and then doing the cubing of these files and for getting the final file for science. I would like also to mention, I have to say it at least, that reducing HiKITS data was one of the key tasks for the PhD student that I have in Cototel with University of Autónoma de Madrid in Spain. And he was going to come work with me last year, but because of the travel restriction, it has been not possible, and this has been very much delayed. Okay. But let me show you some few quick examples. So processing all of this, imagine that this the RSS that are coming from 2D FDR, and we do the throughput correction some small wavelength correction that have been also seen in SAMI, that it is important to really get it right. Correction for extinction, sky subtraction, telluric correction, and removing some artifact. And you can see that the cleaning process, it is quite effective. And for some of the spectra, they are really, really good. We see plenty of emission lines, even the Paschen lines here in the infrared. And also an example of alignment and performing the ADR correction, because we don't have an atmospheric expression correction in Koala, so we have to do it in software, and that is also working extremely well with the offsets that are particularly what we have been given at the telescope in different stage. And something that I took particularly care, it is trying to get the best absolute flash calibration that we could achieve using different flash calibration stars during the night. And particularly this plot here shows the result of 3 different stars, the calibration for the response curve. Each of them, so one was obtained at the beginning of the night, the other one was in the middle of the night, and the last one at the end of the night. It was a very good photometric night, and they agree in 0.5%. So I was extremely happy when I saw this all happening with coming with the code. Let me quickly summarize the specific science of objectives for HiKIPS. One of the main things that I really want to is to emphasize the analysis of the gas, of the ionized gas, to map precise chemical abundances. And when I'm talking about chemical abundances, I'm not talking only about oxygen, but also nitrogen, neon, argon, sulfur, and iron in some of the cases. And the power that we are going to have in many cases, it is that we are going to be using the direct method that considers the electron temperature, and not only with the famous oxygen-free auroral line 4363, that it's what usually only some people are able to do, but we also have
2 minutes, Michael. 2 minutes.
Thank you. We also have some few other faint auroral lines that are going to be key in order that we can establish better the properties of the ionized gas. Also, as in the same way that very well Sam explained, I don't have to do this now, about how to use the absorption lines and stellar continuum for understanding and studying the stellar population, and there have been the stellar metallicity too. That is something else that we want to get, analyze the kinematics, the stars and the ionized gas, and computing modeling of the chemical evolution of galaxies with detailed chemical evolution models, the efficiency of the conversion of gas into stars. For that, it's very important that we have the optical and the H1 data. And of course, and that is another very important thing, it is exploring the scale relationships in dwarfs, that still many of them are not very well known. And we need all these resolved data for doing that. I'm going quickly to skip this because I don't want to say much. It is just one example of one data cube and one of the metallicities, and deriving quickly the metallicities. And another example, it is this blue compact dwarf galaxy that we have been able to get very nice mosaics of that. And I particularly like this object because it is one of the many first objects that I observed with the compact array. And I detected this very long tidal tail with this object. Here at 50 kiloparsecs, it is an even smaller galaxy, and now thanks to HiKIPS, we have been able to determine the metallicities of these, the gas phase metallicities of this object, that is at least 0.3 dex lower than 1230, the main galaxy, meaning that it is an independent object. It was not something that it was in the object. Finally, let me quickly say that HiKIPS is an excellent science case for BlueMUSE. BlueMUSE, it is a new instrument that for the 8.2 meter VLT, and that we are going to, the phase A of this project is going to start next year, and it is going to be very similar to MUSE, but it will have a bit larger resolution, spectral resolution, and definitely moving to the blue in order that we can get not only this part of the spectrum that we get from the MUSE now, but all the other very important parts that is critical for understanding the H1 regions, the interstellar medium structure, stellar population in nearby galaxy, and so on. And with that, I will give you the summary that is connecting gas, star, and metals are key clues for understanding galaxy evolution. And well, if you are interested in HighKids, please let me know, and I will keep you informed about it. Thank you.
Thank you, Angel. We have time for 2 short questions. Maybe stop sharing screen so that Julia can already set up. So the first question I'll throw on to you from the Slack is from Mike Creel. To what extent does shot noise influence your flux measurements, or is that easy to calibrate for?
We are using not only one observing, no one pointing, but usually several pointings, and that minimizes a lot the noise. And the noise, at least in the flux stars, it might be 5-6 order of magnitude, the level of the noise when respect to the very bright stars that we are observing for that. I'm not sure if I'm able to answer your question in that sense, but believe me that the noise level in the reduced combined cube for the calibration star, it is quite low.
Okay, and I can make this a yes or no question from Katie. Does PyKoala fit the spectrum and output emission line maps, or do you use something else for that?
I wish it would be able to do that. Right now, PyKoala is mainly for creating the data cubes that you can use for science in whatever way you want to. Now, there is a way of very first approach that I try to include of identifying the brightest emission lines, but nothing else. It is not doing any further analysis. It has some little tools, but not the real thing that you need for that, for the science.
Okay, thank you, Angel. And with that, we'll move on to the next talk by Giulia Santucci, who is at UNSW, where she's doing her PhD. Julia, please take it away.
Thank you, Jesse. Hi, everyone. Thank you for having me here today. My name is Julia, and as Jesse said, I'm a third-year PhD student at the University of New South Wales, working with Sarah Brown. So today I'm going to talk about my most recent PhD project focused on reconstructing the internal mass distributions and the orbital structures of semi-massive galaxies using Schwarzschild orbit superposition dynamical models. But before going into that, let me just give you a bit of a background and tell you why we do this. So our current understanding of galaxy formation suggests that galaxies form in a two-phase process. And during the first phase, before redshift 2, galaxies become more massive by forming stars in situ, so in the inner region. After redshift about 2, we have the galaxy star, the outer regions of galaxy stars to assemble by accreting ex situ stars. So stars form in external galaxies through mergers with other galaxies and galaxy interactions. Now, the evidence of this formation scenario are predicted to be preserved in the stellar population radial profiles and in the 2D kinematics of local galaxies. So for this project in particular, I've been focusing on the 2D kinematics, applying Schwarzschild models in order to reproduce the internal structure of galaxies and better understand how they form and how they evolve. This is because the merger history of a galaxy is thought to be one of the major factors that determines its internal kinematic structure, the internal kinematic structure of galaxies. So let's have a look at what Schwarzschild models are first. So Schwarzschild models are orbit-based dynamical models that can be used to reveal orbital and kinematic substructures in galaxies. So the explanation that I'm going to give you now, it's very, very simplified. There are lots of things that go into the, if you're interested in the details, please let me know. I'll be happy to talk about that with you. But just to give you a brief and simple explanation, we need 2 main ingredients. One is an image of a galaxy that could be, for example, in the R band, and stellar kinematics derived from integral field spectroscopy observations, like the ones that you see here. And the models that we have from Schwarzschild will include all the kinematic information that we have, not just velocity and velocity dispersion, but also H3 and H4. Now, once we have these ingredients, we can then start by creating a suitable model for the underlying gravitational potential. We do this by using a combination of three components: a stellar component, a dark matter component, and a central supermassive black hole. This is where we need the image of the galaxy, because from that we can derive the intrinsic stellar luminosity density, and then we can convert that into a stellar mass distribution. So once we have a suitable gravitational potential, we can start constructing the orbit libraries. So we calculate a representative library of orbits using the gravitational potential previously modeled. And to do that, we start following, we do a numerical integration of a single orbit in a sufficiently long time so that the density of the orbit converges to a fixed distribution. So we have four main types of orbits that are used: a set of short axis and long axis tubes, a set of box orbits, and a counter-rotating set. Once we have all these different types of orbits, we can weight them in order to reproduce the observable. So we'll weight the different orbital contributions in order to match the observed values, as you can see here. Once we have that, so once we found the best fit model, and you can see here an example, we have the observation maps on the top row and the model maps on the bottom row, luminosity distribution in the first column, line of sight velocity in the second one, and velocity dispersion, H3 and H4. This is just an average galaxy that I had in my sample. It's not the best one, it's not the worst one, but it's still quite good. So the model reproduces the observable quite well. Once we have this, then we can derive the intrinsic properties of the galaxy. For example, we can get information on the intrinsic shape. This is not just the projected shape that we see, but the real shape of the galaxy. And then we can get information on the internal mass distribution. And we can also divide the galaxy into different orbital components. And for our galaxies, we divided them into four components: a cold component that is dominated by strong rotation, a hot component that is dominated by random motions, warm component that is kind of in between these two, and then a counter-rotating component that is similar to the cold and warm component, but rotating on the other direction. So we applied these models to a sample of galaxies from the SAMI Galaxy Survey. You already heard about SAMI quite a lot, so I won't spend too much time on that. But the important thing here is that the SAMI data is, since SAMI is an optical integral field spectroscopic survey, we have about 3,000 galaxies in the local universe with data cubes as observation. So we don't have just one spectrum per galaxy, but we have, for each pixel of the image, we have one spectrum. And so we can get the radial information that we need for the 2D kinematic maps. So all the properties that we derive for the galaxies in our sample were done within one array. And this is due to the coverage of the data coverage that we had. So one array is one effective radius, and it's the radius within which we have half of the light coming from the galaxy. So for our final sample, we selected 124 passive galaxies. They are our primary sample. And we derive for these the intrinsic properties within one array. So let's start from the shapes. We found that most of the galaxies in our sample have oblate shapes, about 83%. We did not see any prolate galaxy, but we found 17% of the galaxies with triaxial shapes. Now, if we look at the distribution of the shapes with stellar mass, as you can see here, we have 3 panels with prolate galaxies, triaxial and oblate versus stellar mass. Especially if we look at the top panel where we have the fraction of non-oblate galaxies, so in particular here is just triaxial galaxies, you can see that the fraction increases with increasing stellar mass. In particular, in the highest mass bins, we reach up to 25% of the galaxies being triaxial. And so we have a turning point that is for galaxies with stellar mass above 10 to the 10.75. And this result point to high mass galaxies being more likely to be triaxial compared to low mass galaxies, or at least lower mass galaxies. And then the other information that we could get from the models were, as I was saying before, the internal mass distribution. So we had a look at that as fraction of dark matter for our galaxies. You can see here the galaxies have been binned in 4 mass bins. And for each of them, I plotted as crosses the median value, with the error bars being the 1 sigma scatter around that value. So there's a slight trend of increasing fraction of dark matter with increasing stellar mass. And again, this happens when the stellar mass is above 10 to the 10.75, so that high mass galaxies have higher fraction of dark matter compared to lower mass galaxies. Well, in this case, even lower mass galaxies have kind of higher fraction of dark matters, and we retrieve the U shape that we've seen in literature before. Now, as I said before, we divided our galaxies in 4 different components, orbital components. So you can see here the orbital fractions for each component. The red diamonds are hot orbits, the orange circles warm orbits, blue triangles are cold orbits, and green squares are counter-rotating orbits. So again, galaxies have been divided into 5 mass bins, and the bold points show the median value of each mass bin, with error bars representing the 1 sigma scatter around the median value. So you can see from the plot that the fraction of hot orbit increases with increasing stellar mass, and at the same time we have, in a similar masses, we have that the warm orbits start decreasing with increasing stellar mass. While for the counter-rotating orbits, we don't really see any change for them with increasing stellar mass, but there is a slight decrease of cold orbits with increasing stellar mass. This means the galaxies higher masses, since they have a high fraction of hot orbits, they're more likely to be pressure supported than rotationally supported. So here is just a quick summary for that. And so putting everything together, what we have is that for the galaxies in our sample, we found that the most massive galaxies are more likely to have triaxial shapes compared to galaxies of lower mass, and then more massive galaxies have higher fraction of dark matter and are mostly pressure supported with a really high fraction of hot orbits, up to about 80%. While for galaxies of lower stellar mass, warm orbits play a significant role. So this means that the trends that we see in the inner parts of passive galaxies, because again, this is within one array, are consistent with the formation paths of early type galaxies, where slow rotating galaxies assemble near the center of massive dark materials via intense star formation at high redshift, and their evolution is then dominated by gas-poor mergers. And then galaxies these galaxies are more likely to be triaxial and more massive, in agreement with what we find. And by comparison, low mass, fast rotating galaxies, so dominated by, in our case, warm orbits, are more likely to grow via gas accretion, and their structure shows similarities with that of spiral galaxies. And with this, I'll stop and I'll be happy to take any questions. Thank you.
Thank you, Julia, for that wonderful presentation. We have questions on the Slack. The first one I'll mention is from Sabine Belstadt. She says, the shapes that you recover from your modeling, are they the shape of a purely stellar component, or does that also include the dark matter component?
So again, they're just within one array. So it's going to be so the stellar component has a great part in that, but it's the total shape of the galaxy. So it's for both components.
Okay, the next question is from Emily Wisniewski. Did you look at the internal shape or orbital fractions with relation to age or metallicity?
Not yet, no, but that's actually a really great thing to do. And has been done before by, of course, other studies, not me personally, but yeah, that would be great to have a look at, because I had a look at the metallicity and age of these galaxies separately, but not together with the dynamical modeling as well. So yes, that would be a great next step.
Okay, and while Steve sets up his presentation, I'll put the question from Matthew Collins forwards. How do these results compare to simulations?
That's a very good question. So for the shapes, the simulations predict that there are many galaxies that have prolet shapes, but so those that do have prolet shapes usually have very high masses, and we don't reach those high masses. So I think it's normal for us not to see many of them. We had a couple of galaxies that were kind of in between, and so considering that there's still a certain amount of errors that we can get, uncertainty that we can get there, some of them might be borderline. But for the rest of the galaxies, the percentage of shapes, it's actually in good agreement with simulations. The same for the fraction of dark matter. Also with previous studies, there are observational studies. And for the orbits, so I couldn't find any study with an actual fraction of orbits on simulation apart from there's just one that I found. So if you have any, please let me know. I'd be happy to have a look at it. Actually, sorry, two of them. But so the ones that I've seen, they don't define the orbital components in the same way that I do. So it's a little bit difficult to compare them exactly. And the mass range of the galaxies is still a bit different. But still what we see is that, what we see, our results with what they find is still quite in agreement and comparable, consistent. Yeah.
Okay, thank you, Julia. There are more questions on the Slack, so I encourage you to have a look there. I hope that everyone can join me in thanking Julia here. And then we'll move on to the last talk of this session, which is by Steve Prabhu. And he will be talking to us about space surveillance using the MWA. Steve, please take it away.
Can you hear me?
Yes, perfect.
Cool. Hi, everyone. I'm Steve. I'm a third-year PhD student here at Curtin Node of ICRAR, and I'll be submitting my thesis next month. So I'm here to talk about my PhD project, which is on performing space surveillance using the MWA. So the working principle here is that the MWA can observe in FM frequencies. And because you have lots of FM transmitters throughout the world that are constantly transmitting FM signals, you can detect satellite reflections of these FM signals using the MWA. And that's how we go about doing space surveillance. Okay, so what's the problem here? Why do we have to do space surveillance? It's been predicted that when the volume density of human-made objects in a given orbit, when it increases past a critical value, it can lead to cascading collision event scenarios called the Kessler effect or the Kessler syndrome. And in the event of Kessler syndrome, you end up destroying all the objects in a given orbit and you render it useless for future missions. And the only way you can either prevent or delay the onset of Kessler syndrome is by doing space surveillance. The graph on the right shows the growth rate of human-made objects as a function of time, and you can see the rapid increase. So it's more and more important to do space surveillance. And this is like a brief introduction to MWA. MWA is a radio interferometer located at the Murchison Radio Observatory. So that's where ASCAP is, and that's where you'll have SKLO in future. And it's in the desert in Western Australia. And each one of these things are called tiles, and there are 128 of them spread across 5 kilometers. And I'll be using the MWA as a passive radar throughout this talk. Okay, so how do we do our detections? So we do difference imaging of MWA sky images. So these are 2 consecutive 2-second snapshots of the MWA sky as seen by phase 1 MWA. The big emission region here is Vela. And when you subtract one from the other, you remove all your radio sources, static radio sources, and along with the confusion noise, and anything that is varying and spatially moves appears as a streak. So the streak shown here is ISS as detected by phase 1 MWA observation. And these are streaks from few other satellites. The one in the bottom right is from a CubeSat, and it appears brighter than the ISS. And I'll get back as to why in a future slide. And then we phase track these sources through our observations, and we plot dynamic spectrum plots to understand these signals better. So this is the dynamic spectrum for the ISS. Your x-axis is frequency, y-axis is time. You can see the different FM channels reflected by the ISS. Many of them were identified to be transmitters from Perth and Geraldton. And these are dynamic spectrum plots for few CubeSats. So CubeSats are allowed to transmit at 144, 146 megahertz for downlink telemetry, but these CubeSats, probably because of malfunctioning hardware, they were transmitting all the way down into the FM band up to like 85 megahertz. And that's the reason why in the previous slide, the streak signal from the CubeSat appeared brighter than the ISS. And if you, instead of using continuum wideband images, if you were to select a single fine channel that contains the signal, you can actually see these objects even without doing difference imaging or even in fact cleaning. So the moving dot in the top video is a satellite called Alouette. So it's a meter in diameter and it's orbiting at around 2,000 kilometers. And the bright static radio source here is unresolved Phonax-A. It appears unresolved because we only use short baselines. And Phonax-A is one of the brightest radio sources in the MWA sky. And even with Phonax-A in the field of view, you can pretty much see these satellites in fine channel images. The one on the bottom is ISS drifting through Vela in a single fine channel image. So we develop a blind detection pipeline that's fairly automated, and we do like a blind survey of the low Earth environment on archived MWA data. So it's fairly automated pipeline. You just provide the raw GPU box files of the observations of the pipeline and a calibration solution for the night, and it images at every 2 seconds and every fine channel. And we have our own source finding software that does difference imaging and does detections of satellite signals or any time varying signals. So in a single 2-minute observation, you have around 42,000 difference images to search from. And this is an output of a single 2-minute observation. So the big circle that you see here is the entire visible horizon, and in anything that you see as red here is a 6+ sigma detection as made by our blind detection pipeline. And all the blue growing tracks are the predicted trajectories of all the objects within the field of view. So you can see there is like a satellite being detected here by our pipeline, and there is this big red thing going north-south. So that's an aircraft flying over the MWA. And aircrafts are like super bright, and you can see them way outside the primary beam of the MWA. And in an autonomous manner, we query all the objects within the field of view, and based on its altitude, we have different search cones, and we cross-match them, and we catalog these objects. And we do a blind survey on 20 hours of MWA data, and we detect over 70 unique objects over multiple passes. And this is the detection summary of the blind survey that we performed. So the x-axis here is RCS, it's radar cross-section. So it's a measure of how big the object is when observing at a given frequency. The y-axis is how near the object was during the pass. And all the scatter points that you see here are objects that drifted through the MWA primary beam during the blind survey, and all the colored markers are the detections that we obtained. And majority of our detections fall in the bottom right quadrant, which is actually the quadrant predicted by a different paper that we should be able to detect with the MWA. And because we were doing this as a blind detection, we see other stuff as well. So in the left, we see meteor trails. So some of the observations we used coincided with Gemini's meteor shower, and these meteors they leave behind an ionized trail, which often reflect FM signals. So these 3 tracks are meteors, and they also point towards the Gemini's radiant. And another cool thing that we can do for these nearby bright events is that you can split the array into 2 or more subarrays, and using the apparent position of the source, you can do line of sight range measurements. So the figure here shows the apparent offset in the position of an aircraft when you split the array into multiple subarrays. We also have a targeted detection pipeline. So this is where you use some prior information of the object you're looking for, and you stack the signal and you try and increase the signal to noise of faint signals. The first method is called shift stacking. So for example, in the top panel, this big circle is again the entire horizon. And in this observation, the object that we are looking for, its trajectory is shown using the blue points, and we phase track the source through the observation, make small field of view images, and we stack across time. So you're basically integrating the signal across the track, and you start getting like fainter detections that you previously didn't detect. So we ran this pipeline again on our blind survey data, and we search for every single object in this data set in this plot, and we improve the number of detections by a little under a factor of 2. So all the new detections that we get with the targeted search method is shown using white circles. And again, majority of the white scatter points, they fall in the bottom right quadrant as predicted by a different paper. And the other thing that we do is near field imaging. So in standard interferometer theory, you assume the source that you're observing to be in the far field. So you assume, or the wavefront as seen by a given baseline is planar if the source is in the far field, and you derive a 2D Fourier relationship between the sky and the measured visibility. But because of the near field nature of the objects that we are interested in, when you start using longer baselines, they start seeing a curved wavefront. And when you image without applying any correction, it creates like a defocused image with a reduced signal to noise. So we have this software, which is called LeoVision, which calculates the curvature as seen by every single baseline and applies it like a complex phase delay and refocuses the interferometer to a near field position after the observation's done. So we test this on an extended array observation of the MWA. So the object being detected here is ISS. So the short baselines see the ISS as expected because the object appears in the near field, in the far field, and the long baseline image don't detect it because of the curved wavefront that they see. And then we run our software, apply the required phase correction to all the baselines, and you start seeing like a streak-like structure. So this section,
Steve, 2 minutes.
yes, thanks. So this section is just me very briefly commenting on the impact these satellite signals can have on radio observations as performed from the MRO. So the first analysis is, so in this plot here, I combine all the detections that we obtained during our blind survey. So all the plane tracks, meteor tracks, aircraft tracks, plot them as a maximum signal to noise event as detected as a function of azimuth and elevation. So you can see all the like satellite tracks near the zenith, meteor tracks near the horizon, and the big inverted U is an aircraft. And obviously, because we are looking for RFI-like signals, we don't flag our observation prior to running it through our blind detection pipeline. And after that, we take the observations, run it through standard default arguments, the default flagging software is used, and we pretty much recover almost all the events, except few like the event shown inside the green circle that gets flagged, and we recover the aircraft track with lower signal to noise. So the point of this exercise is to show that the default flagging strategies don't really work for FM band observations, and more care has to be taken if you want to mitigate the impact of these signals in radio observations. The one on the right is Starlink. So Starlink is a 40,000 satellite mega constellation that's currently being launched. And in the top video, you see an optical observation of Starlink. I didn't do this, I took this off the internet. And the MWA can also see Starlink after flagging using default arguments because of their FM reflection. So again, FM band observations performed from the MRO need to be like flagged with more care, especially because you have SKLO also being built there, and it's going to be a lot more sensitive to these signals. And this is my conclusion. Thanks.
All right, thank you so much, Steve, for that really interesting talk about everything that we don't want to have in the night sky. The first question is from Andrew Jolly. What was the event between 2006 and 2008 that caused the big spike in your plot on the very first slide?
Oh, yes. So one of the big jumps was when one of the countries tested out their anti-satellite capabilities, which created like a debris field. And the other jump was when two satellites accidentally collided in orbit and created another debris field. Yeah.
Okay, then the last question that I'll put towards you for this session is from Mike Creel. What is the smallest object that you can detect?
So we have detected CubeSats, which are 10 centimeters by 10 centimeters, but not through FM reflection, but because of their out-of-band transmission. But otherwise, I would say something that has like a meter square reflecting area. Or you can also have thin, very small objects, but if they have like an antenna on board, which can reflect FM-like wavelengths, then their radar cross-section would increase, although the physical size is quite small. Yeah.
All right, wonderful. The Slack channel is as full of questions as the night sky is of satellites, it appears. So please take a moment to have a look through there. That concludes this session. Please take a moment as well to have a look at the AGM, which will start probably as we speak. So please join me in thanking all speakers for this session one more time. All right, thank you.
So the AGM will commence in about 5 minutes' time, so that gives everybody a chance to go and get some lunch or afternoon tea, depending on your location.